Let's continue our discussion of electron spin in quantum chemistry. One thing that's really easy if you're trying to determine what spin multiplicity to put into a quantum chemistry program is if you know the term symbol of the state that you're trying to model with a computation. So if you have a smaller molecule that has some kind of symmetry to it, all the OH bonds are equivalent in water, for example, so it has some symmetry. Anything like that, you can have what's called a term symbol, which is just a way to encode the symmetry that the state, the electronic state, has that you're trying to model. And they generally have this format. You have some kind of symbol X, and then it's got a superscript on the left, which only takes certain allowed values. It has to be 2s plus 1, the spin multiplicity. So you put the multiplicity on the left as a superscript, and then X is some kind of symmetry label that comes from group theory. And some examples would be singlet sigma G plus, or delta, or a doublet pi, or a triplet B1U, or a singlet AG. These are all various term symbols for some small molecules. So if you know what state you're looking for, then you can immediately know that multiplicity is just whatever the superscript is. Okay. Now let's talk a little bit about d-metal complexes, because these can be a little trickier than closed shell molecules, which are just singlets, or radicals, which are just doublets. If it's a d-metal complex, then life might be a little more complicated. So, for example, suppose I have titanium surrounded by 6 waters, and with the entire molecule having a 3+ charge. Well, these ligands in these kind of complexes can form either rather weak interactions with the metal in the middle, or rather strong interactions. So there's kind of a spectrum depending a lot on the type of the ligand. But in this particular case, we imagine intact water molecules that are just kind of partially donating their lone pairs from the oxygens to the titanium. So it's a kind of a weak dative bond sort of situation. And we do imagine the waters retaining all of their electrons, basically, and just kind of partially sharing them a little bit. So here's a little picture of this. I've got titanium where I've got the waters around it in a kind of an octahedral arrangement. And the whole thing has got a 3+ charge. So if I do assume that the ligands, in this case the waters, are holding on to most of their electrons, then that also kind of implies that the metal is the less electronegative partner, because it's not ripping electrons off of the waters, for example. So I use these assumptions when I'm figuring out how many d electrons are there in the complex. And I also obviously have to look at the charge state of the entire complex. So 3+ will be very important. So what about titanium? What is it normally? Well, normally it's got an argon core for an electron configuration, and then it's 4s2 3d2, as you could see if you look it up on periodic table. That's where it's situated. So it has in the bare atom 2 d electrons, or a d2 configuration. However, here we're going to do something a little different. We're going to assume that in an inorganic or organometallic complex, that the metal is the least electronegative site, and that if I'm going to rip electrons off, they're going to come off the metal. So the 3+ charge, if I need to take electrons off of anything, comes from the titanium. And the waters are all neutral, and so they do need to come off the titanium, all 3 of these. So let's take electrons away. But then there's a second concern. There's a trick. So unlike the Aufbau principle, when I fill up electrons just to get the bare atom electron configuration, now when I'm in a complex like this, I flip the rules a little bit, and I assume that I take electrons out of 4s before I take them out of 3d. So that's a kind of a twist on the normal rules, because normally we fill 4s first and then go on to 3d. But for ripping electrons off, we're going to rip them out of 4s first before we rip them off 3d in complexes like this. So let's do that. So I've got 3 electrons to remove if I need a +3 charge. I'm going to take 2 away from 4s, and then there aren't any more in 4s, so now I have to take 1 more out of 3d. And so that winds up with a 3d1 configuration overall. So titanium is a d1 configuration, and that is then what goes into the next step to figure out what the spin of this whole complex is. So here's a molecular orbital diagram. For these complexes, it involves a kind of an extra step. So normally you have, in a diatomic molecule, say, you'd have 1 atom on the left and 1 atom on the right, and in the middle you'd show the molecular orbitals. Here I've got 1 atom on the left, titanium. I've got the molecular orbitals on the right, but in the middle. But on the right, I've got all these waters. So what I've done is I've already mixed and matched atomic orbitals on the waters to form molecular orbitals, but just on the ligands. And furthermore, I've symmetry adapted those to the octahedral point group that we're looking at. So that's what are called these group orbitals over here. And you can see that there's 6 of them because there's 6 ligands, okay? So, you know, things like the oxygen core electrons, they're buried inside and they're not showing up on this MO diagram because they don't participate with the titanium. And likewise, the OH bonds also are sort of not particularly participating. It's, I think, mainly oxygen lone pair character that's going into these group orbitals that then are symmetry adapted and available to interact with the titanium. Okay, so these are basically symmetry adapted lone pairs. And there's 6 of them because there's 6 interactions, 1 for each water with the titanium. Okay, so there's 6 orbitals, ligand orbitals, forming 6 molecular orbitals when they combine with the d orbitals. So that stabilizes the ligand orbitals compared to what they would be in a free set of water molecules. And the lone pairs are all filled, so these molecular orbitals are all filled. And so I can now kind of not worry about them anymore. What happens to the d electrons in titanium? Well, they can mix with these ligands to form molecular orbitals, but they don't mix particularly much. Some of them, the energy of these just kind of comes straight over. And notice that only happens for 3 of them. And there were 5 d orbitals. So what happened to the other d orbitals? Well, they go up here. So this gives me a total of 5 orbitals. 1, 2, 3, 4, 5. And they split into 3 of them, which has a label T2G, and 2 of them, which has a label EG. That's mainly what happens to the 3D orbitals. And you know, some little character of the 4p's and 4s's mixes with these group orbitals to form these molecular orbitals and help stabilize them. But again, those are all filled, so that doesn't matter if I'm just trying to figure out the spin, because remember, any orbital that has 1 alpha and 1 beta in it, those cancel out as far as the spin goes, and they don't contribute to any net spin. But I had a D1 configuration from the previous slide, so I put 1 electron here, and it kind of comes straight across, and I have 1 unpaired electron there. And these other things wind up not mattering for the spin because they're not occupied. And so it looks like a radical. There's 1 unpaired electron, and so I would expect the spin to be a doublet because I have 1 spin of 1/2 that isn't paired with anything. So if I have a doublet, then s equals half, 2s plus 1 equals 2, and I put 2 in the program when I'm setting up the calculation. Okay, so hopefully that gives you a little insight on what happens to some of these complexes. Let's look at one other example. Suppose I had iron with 6 NO2 ligands and an overall 3- charge. Now, the NO2 comes as an NO2- in this complex, and there's 6 of them. So I get a total of -6 charge from the ligands. And if the overall charge is -3, then for charge to equal out, then the iron obviously is +3, and then that would give me a total charge of -3 on the entire complex. So iron's in a +3 oxidation state, which is a normal oxidation state for iron. It's a ferric ion that interacts, so that's totally fine. What's the normal electron configuration for iron? Well, it's argon core, 4s2, 3d6, and that would be the isolated atom. If it's in a +3 oxidation state, then I take 3 electrons out, and again I do this funny thing where in an inorganic complex or organometallic complex, I'm going to rip out the 4s electrons before the 3d, so that's a quirk you have to remember with these problems. So I take these 2 off, but it's +3, so I need 1 more, so I take 1 out of here, and that gives me an overall D5 configuration. Okay? And in an octahedral environment of ligands, sometimes people call this a crystal field or a ligand field, then the d orbitals on the central metal split like they did in our previous example of titanium with 6 waters around it. So they split this way in the octahedral complex. If it was a different shaped complex like square planar, then it would be a different story. But octahedral, they split this way. T2G on the bottom, that's 3 orbitals, and EG on the top, that's 2 orbitals. And I need to now put 5 electrons in this thing, okay? Is this a Hund's rule situation? Is it not a Hund's rule situation? Well, let's think about this for a second. I've got a couple choices. I could either go ahead and use all 5 of my electrons as unpaired, and that would assume that the energy of this EG isn't very high up. So if there's a small energy gap, then I could say, you know what, it won't cost me much energy to go ahead and put single electrons in these, and so maybe the spirit of Hund suggests that, as long as there's a small energy gap here. We might call that energy gap delta, okay? And so for a very, very tiny delta, you would think Hund might imply that you would do this, and goodness, what kind of spin is this? I got an awful lot of unpaired electrons. Well, I've got 5 unpaired electrons. Each has a spin of 1/2. So that gives me a total of s equals 5 halves. And if I put that in 2s plus 1, I get 6, which is called a sextet. You know, if I have 1 unpaired electron, that's a doublet. 2 unpaired electrons is a triplet. So the multiplicity is basically the number of unpaired electrons plus 1 if they're all pointed up. So here there's 5, and that's not a quintet, it's a sextet, because you got to add 1. So sextet. What if this energy gap was bigger between the T2G and EG orbitals? If it's sufficiently big, then I would go ahead and start pairing up the spins in the T2Gs before I hopped up in energy to the EG. And so that's this situation on the right. And because there's 5 electrons, I have to pair 2 of them, make 2 pairs. And then I've got 1 unpaired one. So these guys, because they have an alpha and a beta, they kind of cancel out and don't matter for the spin. This one doesn't cancel out, and there's only 1 of those, so it's a doublet. So I have these 2 possibilities. How do I know which one it is? Well, I would need to know how big this gap is. How would I know that? Well, there are some rules of thumb, so if I learned a little more about inorganic chemistry, I could have a guess at this. And it turns out NO2- is what's called a strong field ligand, which means it gives you a large delta. And so knowing that, then we would expect that it's the situation on the right is going to be more accurate, and so I expect this to be a doublet. if I didn't know much inorganic chemistry and had a hard time looking this up or whatever, I could potentially run the calculation and try to get the calculation to tell me, but I would have to run both of these possibilities. And the user would have to put in sextet and doublet, do two separate calculations, and then see which one has a lower energy. And then that would give you a clue that probably that would be it. Okay, but in this case, the low spin or doublet configuration is going to be the most stable. You can look these up sometimes, and there are what's called Tanabe-Sugano diagrams, which tell you about the ground states and low-lying excited electronic states of some of these inorganic complexes. So in the D5 case, there is such a Tanabe-Sugano diagram, and we could look this up. And it's plotted as a function of delta, this delta gap that I just had on the previous slide, okay? And you'll see that for smaller deltas, the ground state in a complex looks like a sextet A1. But if I go to much larger deltas, then it swaps and I wind up over here. So that's the high spin case. And then over here, this is the low spin case for bigger delta situations, which we said NO2 minus would lead to. So these diagrams can be helpful if you kind of know what ligand you have and what approximate delta you would expect. Then you can kind of look to these for guidance about what spin to expect. And these are also nice because then they tell you things like excited states as well, and you could use those if you were interested in the absorption, for example. In fact, let me talk a little bit about excited states. Let's leave inorganic complexes behind now. Hopefully that gives you a taste of how they work. Probably you would want to learn a little more about inorganic chemistry if you were going to do a lot of calculations on those. But let's think about excited states for a second. And I have a talk only about excited states. That's a separate topic. But just for a couple slides here, suppose I've got a nice, well-behaved closed shell molecule, okay, and it absorbs radiation, and that radiation allows me to get some energy. So a photon comes in, and the photon disappears, but its energy can't disappear, it's conserved, and that energy goes into creating a quantum leap from one state to another, and we could draw this pictorially as having an electron hop up into a higher energy molecular orbital, okay? And that can certainly happen, all right? And suppose it does. Then I've got an unusual electron configuration. I'm not obeying the Aufbau principle anymore. Aufbau principle just works for your lowest energy state, your ground state of an atom or molecule, but this isn't a ground state. I've got extra energy that's caused electrons to be promoted to higher energy levels. So what do I do if my electron configuration looks like this? And what spin does this have? In fact, I have a bit of a quandary right off the bat. If I know I have enough energy in this photon to promote a jump between this level, which might be the highest occupied molecular orbital, and this level, which might be the lowest unoccupied molecular orbital, how do I know I moved the beta spin like I did? Why didn't I move the alpha spin, for example? Maybe I should draw it like this. Well, these two diagrams really have exactly the same energy, okay? If I somehow could do a Slater determinant like this and do a Hartree-Fock calculation on it, which is actually a hard thing to do. I'll say more about that in a second. But if I somehow did that, this guy has the same energy as this. Or if you think back to the pseudo-classical interpretation of Hartree-Fock energies, I could write down the energy of this in terms of H's and J's and K's, and I'd see that the energy of this in terms of those quantities is the same as the energy of that. So how do I pick? Which one do I go with? Well, because they're really equivalent, what I need to look at is a combination of the two. I really need both of them, because leaving off one of them is leaving off sort of half of the situation that happens. And this is called an open shell singlet. So I started with a singlet, I wind up as a singlet. Absorbing a photon means if I start in a singlet state, I wind up in a singlet state. So I preserve the spin unless other things happen that we're not worrying about right here. So I do wind up with the singlet state, but I've got two determinants that are equally good to describe it, and I ultimately need both. And this is called an open shell singlet situation. And it turns out what I want is actually the plus combination of the two. Now, to make the wave function normalized, if my molecular orbitals are normalized and my Slater determinant is normalized, and if this diagram represents one Slater determinant, and if this diagram represents one Slater determinant, then for the overall wave function being an addition of these two to be normalized, I need to put a little 1 over square root of 2 out in front to keep all things normalized. So that's fine, I'll throw that out there, it's no big deal. For a plus combination, this will be an open shell singlet wave function with s equals 0, because it's a singlet after all, and anytime s equals 0, m sub s has to be 0. Okay? Now, you might see in some textbooks they might put a minus sign, and that might also be correct. How can they both be correct? It depends on exactly how you interpret these diagrams. When I draw these, I usually count orbitals by going through the alpha spin orbitals first and then listing all the beta spin orbitals. So for me, I would list this one first and then that one, but in this one I would list this one before I list that one, because that's just me, I just do alpha electrons first. I wrote a program that does configuration interaction when I was a graduate student, and I made that rule for that program, and it works great, and so why not? The other rule you could have is you could list them all in energy order, and if you do them in energy order, then this determinant has a column swap compared to the way I interpret it, and the column swap on a determinant gives a minus sign, and so then you need the minus sign here to cancel that. So different conventions lead to different signs, but I'll stick with my convention. Okay, so then the plus gives a singlet. But then what if I did a minus sign? What would that be? Well, you could do that. And it turns out that's going to be a triplet state. So minus sign, same determinants, is what you might call a low spin triplet. Of course, the spin is fixed, it's s equals 1, but I mean the projection of the spin on the z-axis is low in magnitude, it's 0. Why is this m sub s equals 0? Well, remember, m sub s, you just count alpha and beta. And 1 alpha, 1 beta, they cancel, m sub s equals 0. Okay? So that's easy. So it's the m sub s equals 0 component of a triplet, and that component, it turns out, requires two determinants to describe it, which is how it is. If I had the high spin case, then I had 2 alpha electrons. That's the m sub s equals 1 component of s equals 1 triplet. And if I had 2 beta electrons, that would be the m sub s equals minus 1 component of the triplet. Remember, triplets have 3 components, of course. That's why it's called a triplet. And this is the one smack in the middle with the m sub s equals 0. So, with these two determinants, if I add them in a plus sign, I get an open shell singlet. If I add them in a minus sign, I get a low spin triplet. Can we deal with these in quantum chemistry? Yes and no, depending on the situation. If you had some kind of situation where your ground state looked like this, which is a little rare, but it's not impossible, you'd be kind of out of luck because most programs can't handle a linear combination of 2 determinants when doing a Hartree-Fock molecular orbital calculation or a density functional theory calculation. It's just not coded into the software. Now for these open shell singlets or low spin triplets, because you have a fixed combination, it's just plus or minus and you've got known coefficients in front of them, it's a kind of a special case, and you could imagine that if you were willing to work hard enough, you could derive a few equations and code this up. And you can. but nobody does. So it's kind of just not available to literally do an open shell singlet exactly the way I have written it. Now, theoretically, all the components of a triplet, ought to have a same energy, and so you could maybe get away with saying, well, I'll just do the high spin component of the triplet. So maybe there's a solution there, but that's not necessarily the case for open shell singlets. This is not necessarily the same. In fact, it's not the same as a closed shell singlet with only one relevant determinant. So if you have a situation like this is a little tricky. You could do this as a special case of a more general procedure, and that would be the MCSCF procedure. So multi-configurational self-consistent field is an approach that can work for bond breaking and diradicals and a lot of things. And it would be able to handle this. It would be able to weight these with something different than equal weights, but if they needed equal weights, it would be able to pop that out. So you could use an MCSCF program, but those are a little bit more complicated to use. If this literally came up when you were trying to model an excited state, then you're okay, because it's such a critical feature to describe homo-to-LUMO transitions that the authors of excited state procedures in quantum chemistry programs have coded this up where it does fall out. In fact, it kind of falls out naturally because you're doing configuration interaction, or the way you code up time-dependent density functional theory allows for these kind of plus and minus things with equal weights. So that's okay. If you have a singlet excited state that looks like this, then you do a CIS calculation or a TD-DFT calculation starting from closed shell ground state, no worries. But if this was your ground state, that's where you'd have to go to MCSCF or something, okay? Now, because the software isn't available, if you want to treat something like this as your ground state, sometimes people feel desperation. And probably what they should do is go read up a little bit about MCSCF and do a limited MCSCF. In fact, you can limit an MCSCF sometimes to only 2 configurations, and that's called TCSCF. And, that kind of thing could get at what you need to do. Okay, but a lot of times people don't have the patience for this. And they say, you know what, I'm just going to do one of these determinants, and I know I can only pick one, so I'll just pick one, and they might pick this, they might pick that. They say, you know what, it'll be fine. Let's just pick one of these determinants, and who needs the other one anyway? Let me try to convince you this is very bad. Okay, so just recapping, the singlet, here's my term symbol kind of notation. Here's a singlet with a 1 and a superscript on the left. The singlet looks like the plus, and the triplet looks like the minus, okay? So suppose you were desperate and you tried to do a calculation where you had something like this, where an alpha electron's in one orbital and a beta is in a different orbital and they have different energies, and you said, yeah, that's the best I can do. I'm going to do that. Well, let me try to convince you that this determinant, if I only do one of them, is 1 over square root of 2, the singlet, this guy, plus the triplet, okay? And I can prove this like in one line or something. Let's assume it is true and then check if it's consistent. If it were true, then I could take this singlet wave function here and insert it there. And if I could insert this triplet there, so let's do that. Let's insert those two. So now I've got this. This 1 over square root of 2 was outer, so it stays outer. Then this one was inside here and part of the singlet, so that's that. And then that 1 over square root of 2 is part of the triplet, so that's that. Singlet has a plus sign. Triplet has a minus sign. And let's just add and subtract. All right, well, I've got this determinant twice. Here's one, here's another one. I've got 1 over square root of 2 times this, plus another 1 over square root of 2 times that. So that's 2 over square root of 2. And then outside that, I've got a 1 over square root of 2. So that's 2 over 2, or I've got one of these guys. What about this one? Well, I've got this one minus that one. So the coefficients don't matter because they're all the same. but they'll cancel. So this cancels that, so he goes away. So this thing winds up equaling that guy, which is what I asserted. I asserted that this was equal to that. Now with a little math, you can see that, yep, sure enough, it really is equal to that. So what's the upshot of this? Well, the conclusion is this one determinant is a linear combination of essentially 50-50 singlet and triplet, which means this one determinant does not have a well-defined spin. It's actually a 50-50 mixture of a singlet and triplet, so it doesn't have a spin. It's like some kind of hybrid monster of part triplet, part singlet nature. And if you were interested in using this to compute any properties that had anything to do with the spin, then potentially they could be garbage because it doesn't have a spin. It has half this spin and half that spin. Or another way of looking at it is if the real wave function looks like this, and my program only allows me to do this, I have basically half a wave function. And if that sounds bad, it is bad. So lots of people do this because their program won't let them do this. But you have to take the answers with a giant grain of salt because you have half the wave function that you ought to have, which is a very iffy kind of scenario. All right, let's switch gears to another situation. What if I had diradicals? Diradicals are like radicals, but there's just two radical centers. So here's a bunch of examples. You have two dots. So organic chemists draw a dot when you have an unpaired electron. So you got all these things with two dots. So you see them in organic chemistry. It's fine. This one is cyclopentane 1,3-diene or Claus's diradical. I worked on that as one of my very first projects when I was a summer student learning about quantum chemistry. So that was kind of fun. Well, if I have these two radical orbitals, then you might imagine in some of these they were in very symmetric molecules. So those radical centers might be symmetric with each other. And if they're symmetric, you might expect the two radical orbitals to have the same energy. Now normally when you do quantum chemistry, you don't deal with a radical orbital. You mix and match all the orbitals to get molecular orbitals that are delocalized over the whole molecule. So the radical orbitals, I would take plus and minus combinations to form molecular orbitals out of those. Okay? And if the two radical sites are very, very far apart, then they can't really talk to each other electronically very much. And then if I take a plus combination or a minus combination, they'll have basically the same energy because there's just no interaction between the two. But if they get closer, then you might imagine a plus combination is going to be more stable because there's no nodes in between the two. And a minus combination will be less stable. So that's kind of what we would expect for interacting radical sites. And I could just draw a little diagram of this. The plus combination of the two radical orbitals will give me a molecular orbital which has a partial bonding character. There's not a bond, obviously, because I've drawn unpaired electrons. So they're not paired, there's not a bond, but nevertheless, it has you could think of it as having a favorable in-phase combination with maybe some, weakly bonding, partially bonding character. And then the minus combination has a node in between, so it has a little bit of an anti-bonding character. And there will be some gap between these that basically should grow as the radical centers get closer and closer and have more chance to communicate with each other. And as they get farther apart, delta should become very small. Now, if delta is very, very large, then you might expect whatever this in-phase orbital is, I would just put both electrons there because the Aufbau principle would tell me to do that. And that would give me a closed shell singlet if I did that. On the other hand, if delta goes to 0, and so these orbitals become degenerate, so maybe the radical sites are very, very far away, then I would expect something like this, a high spin triplet, okay? Because that's what Hund would tell me to do. If delta is in between, then I can get some trickier situations. I could do something like this and have two electron configurations that are relevant. So it could be kind of largely this one, like this situation here, but there might be an appreciable contribution from the case where I take both electrons out of here and promote them into here. And you might think to yourself, well, gee, that is a higher energy orbital, so why would it ever be favorable to do that? Well, that gets back to the idea of configuration interaction. Configuration interaction teaches us that mixing different configurations can lower the overall energy. And if we worked out what the CI energy looks like in terms of these C coefficients, you'd see that, oh yeah, even putting electrons in higher energy orbitals can give me some interference terms that winds up lowering the energy. And if there's a small gap delta, then there could be a pretty substantial weight to this other determinant. So maybe I need to include that. Now, if I did want to include that, I'd need to do some kind of CI or MCSCF or something to allow for a second configuration to enter into my calculation. Or I could get a situation kind of like this, where I have open shell singlet or a low spin component of a triplet. And in general, if it's a diradical, you'd probably go for a two configuration calculation, because if you do this, it turns out by transforming the orbitals, the open shell singlet would wind up coming out of this as a special case in which C0 equals C1. And then by transforming the orbitals, I could get to this picture. So this would be a more general way to do it. But in the limit of kind of non-interacting radical sites, then this description would work perfectly well also. So diradicals can be a little trickier, but I guess you can see that in terms of what's the spin, there's basically two possibilities. If you're in this situation, it's a singlet. If you're in this situation, it's also a singlet, because I'm mixing two wave functions that are both singlets. And if you're in this situation, if you take the plus sign, it's an open shell singlet. So it's a very special singlet, but it's still a singlet. But your program probably can't handle an open shell singlet without special considerations, so that's an issue. Or it might be a triplet. Now, for a given diradical, how do you know if it's a singlet or triplet? Frequently you don't. If you're an expert in diradicals and study them a lot, then you may be able to look at one and tell. But in general, the singlet and the triplet solutions are close in energy, and so a lot of times you have to run calculations on both and let the computer tell you what it thinks is the lower one. And they may be so close that you may have to run higher levels of theory to sort of appropriately describe this. And that can be a little tricky if you're in this two configuration regime, because maybe you need to do some kind of CI or perturbation theory on top of these two configurations being treated with nearly equal weights, and then that means you need a multi-reference method or a multi-configurational method, which gets to be kind of an advanced approach. So diradicals can basically be tough. Let me finish up this talk with talking a little bit about spin pure states and spin contamination. Now, if you have some molecules that contain very, very heavy atoms, then the whole spin idea goes out the window anyway, because it's no longer a valid concept with very, very heavy elements. You switch over into strong spin orbit coupling and eventually into something called JJ coupling, and I'm not going to get into all that. If you're in situations where you have lighter elements, they're not very far down on the periodic table, then we want to have approximate wave functions that correctly describe the spin of the state. And so one way to say that a little mathematically is to say the wave function that you use for your calculation, or that comes out of the calculation, ought to be an eigenfunction of the s squared operator, meaning s squared operator hits your wave function, gives you a wave function back, times an eigenvalue, which winds up being h bar, I think it's h bar squared actually, times s plus 1. Okay? If you're lucky enough to have a closed shell singlet with all the electrons paired, then you're fine, because that is a spin eigenfunction, and with s equals 0, and you're set. Okay? If you're in one of these two determinant cases I've been talking about, where you have plus and minus these guys to get a singlet and a triplet, these, if you had them somehow in your wave function, are pure spin states. Pure singlet or pure triplet. So they're fine conceptually, and if your program can generate them, like in a CIS calculation on excited states, then great, you're set. You have a spin eigenfunction, no problem. If you had, I mentioned this a second ago, diradical, and you somehow did a TCSCF or MCSCF on it or something, and I mixed these two determinants that are both singlets, then the mixture of two singlet determinants is also a singlet. So that's fine. So he's spin pure as well, if I had this description. So those are all okay. What if I had a doublet, like a radical with one unpaired electron? Or what if I had a high spin triplet, like a P2 configuration for carbon atom? And if I put those two electrons in two of the p orbitals, as long as I use restricted Hartree-Fock orbitals, then those will be spin eigenfunctions, and life is fine. There'll be a doublet if it's a radical, or a triplet if it's p2, but at any rate, they're all spin eigenfunctions, so they're totally fine. If I do a configuration interaction procedure like CISD, and I've been careful to make sure that all the determinants that I have all the possible spin coupling possibilities that are necessary to form a spin eigenfunction, then the CI will automatically give me a spin eigenfunction out, unless something weird goes on in my procedure. So a lot of times CI, even if I do the CI with a determinant basis, will give me spin eigenfunctions out if I have all these spin coupling determinants. This is a little bit of a technical thing, but I mention it because I'm on the topic of spin. And you could look this up if you're more curious about that. However, in other situations, I'm not necessarily guaranteed that the result of my quantum chemistry calculation is a spin pure state. And so one way to tackle that is to force it to be by formulating the quantum chemistry problem in terms of what's called configuration state functions. And what these are determinants with the proper plus and minus and weight factors in front of them that combine to form spin eigenfunctions. And so then I do my quantum chemistry procedure using these configuration state functions, and then the result of that is guaranteed to give me a spin eigenfunction. So you can do configuration interaction this way, and then you for sure are guaranteed to get spin eigenfunctions out. In a determinant basis, you may or may not, depending on the particulars of how you set up the problem and what determinants you had access to. What if I did, now the previous slide was all kind of assuming restricted orbitals. What if you don't use restricted orbitals? What if you use unrestricted orbitals? Well, in general, if you do a UHF calculation, there is no guarantee you get spin eigenfunctions out, and typically you do not get spin eigenfunctions out. So out of most UHF procedures, unless they're trivial, like if you somehow ran a UHF on a helium atom, and unless you deliberately broke the symmetry, then you'll get the RHF result back, and that's a different case. But in a general application where you would want to use UHF, like a doublet state or a triplet state, your eigenfunctions are not spin eigenfunctions, okay? And what we say is that they're contaminated by higher spin states. And I can calculate the expectation value, or the average value of this S squared operator, and it ought to give me h bar squared times s plus 1. But in fact, if I use UHF orbitals, it won't give me that. That would be the exact result. It'll give me something that's bigger than that. And that's because my wave function is now contaminated with some partial contributions of higher spin states. Not lower ones, but higher ones. So for example, if I was trying to go for some kind of singlet state using UHF, then I would get some coefficient times a pure singlet state plus some coefficient times a pure triplet state plus a coefficient times a pure quintet state. So I'm mixing in higher multiplicities, and they kind of hop in this pattern. So there's no doublets that contaminate a singlet, but there are triplets. And there's no quartets that contaminate a singlet, but there are quintets. So you kind of hop, like this. So if I had subsequent analysis that involved anything to do with spin, this would be bad because I would have all the wrong spins kind of mixing in with the spin I'm supposed to have. So that would be dangerous. The energies themselves may or may not be okay depending on the situation and how big the spin contamination is. So if you're doing a calculation on a radical and you know it's supposed to be a doublet and you use the UHF because it's easier to converge the orbitals, that's all fine, but you might want to compute the average value of S squared and just make sure that in atomic units it's around 0.75, which it would be for an exact doublet. It's S times S plus 1, and for a doublet, S is a half, so a half times a half plus 1 is a half times 3 halves, which is 3/4, which is 0.75. And if you get 0.79 or something, you say, yeah, well, it's in the ballpark, it's probably okay. And if you got something way, way bigger than that, then you might be very nervous that something went wrong with the calculation. Okay, well, that's all I have to say about spin for now, and hopefully that's a helpful introduction and gives you some guidance in terms of if you're running quantum chemistry calculations, what spin is appropriate for different kind of problems.